Good evening, everyone. Let's see here. Tonight's class might be very short, like till 7 o'clock. Both my wife and I are working, and our daughter is over at the tennis, her tennis thing. And so she'll be done at 7. So she's going to text or call, let me know. And it's a little bit easier for me to, just end class. My wife has like counseling or something. Okay, the other thing is that I changed my mind on some stuff, and I decided that tomorrow we should have a time test on chapter 11. Just the parts that we've covered up to now, okay? Because today things are going to get a little bit more complicated. So on your part 1, and it's going to be available at 6 o'clock. So, and it's 6 o'clock to do at 8:30. Okay. And I'm going to tell you right now what I've put on it so you guys can practice. All right. So the first problem is some kind of a limit, and it's going to be not so obvious what to do. Okay. It's not hard, but the second problem is I give you a series, and I want you to decide if it converges or diverges, and I want you to justify. The third question, I have a sum that I want you to actually find. So this series, you can actually find what the sum is. Okay. And then number 4, I give you a power series, and I want you to find the interval of convergence. Okay. Keep looking up because Mookie Betts is up. He's about as ice cold as Mike Trout. Number 5, another power series question. And I want you to you know, find the interval of convergence. Okay. Number 6, I say, I give you this function, and I want you to find a power series representation for it. Okay. The 7th question is a question that is kind of like how we ended yesterday. Remember that integral that I was doing? And we used the power series to evaluate it. Okay, so I have another integral here, and I want you to find a series that represents the integral. Okay. And then number 8 is another one of these sums that I want you to figure out what it adds up to. Okay, and I will say that number 8 is kind of, it can be real easy or it could be just a nightmare. And so anyways, that will be for tomorrow night. Okay. So, and I'll put this in the announcements after class is over. Thanks, Jeff. All right, so let's do the screen thing here.
Bobby, I have a question.
Yeah.
So once the questions that you talk about right now will be tomorrow during the class.
During the class, like a timed test. Kind of like that first one we did. But I see, I want to separate this material from the new stuff. From what we're gonna do.
Yeah, what about the part number 2?
Okay, so then that'll be next week.
Okay, thank you.
Okay. 185, and we're doing we're going to start here. Taylor series. Oops.
Professor.
Uh-huh.
So is this part 1 and 2 considered as 4 and 5, or this is completely as 4?
This is 1/2 of the chapter 11 exam. I've always been wanting to do this, to change it like this, and because I think it's just too much material. So from chapter 11, and everybody else that teaches 185, everybody else splits it up into a couple. So I wanted to try that out and see. Now, you know, many of you just be waiting for someone to give you the answer and stuff. I get it. But for some of you that are going to be needing this stuff, you know, take a crack at, you know, doing it yourself before, you know, it's too crazy. Okay, so, other things. I was looking at our enrollment, our numbers. You guys would be, if you would be moving on, you'd be moving into 280 and or 285. It looks like we're getting pretty full. And depending on the situation with someone, I might have to take the 180, one of the 285 classes. So I wasn't planning on having those. I just had the 2 in the fall. Okay, so let's do our review real quick. Okay, so we had this power series idea. And it came from the observation that the sum k equaling 0 to infinity of x to the k can be written compactly like this, as long as x, there we go, as long as x is in magnitude less than 1. Okay. Okay, so people like, and this kind of thing had been known for centuries. So people like James Gregory started wondering that, are there other functions that behave like this? If I start with the function, which is 1 over 1 minus x, I can write it as an infinitely long polynomial, like so. Okay, and so, back in those days, people were using this, this geometric series idea to come up with all kinds of stuff. Okay, so we looked at, we end up looking at other types of functions and seeing what kind of series we can come up with for that. Okay, so let's try an example here. All right, 2 different ways to get a series. Okay, so let's suppose that I'm looking for a power series representation for f of x equals 1 over 1 minus x squared. That's probably look more like a 1. Go back to black. 1 minus x squared. Okay. So one thing we could do is we could take f of x, which is 1 over 1 minus x squared, and write it as the product of 1 over 1 minus x times 1 over 1 minus x. Okay. Now, each of these guys, we have a series for. So it's going to be 1 plus x squared plus x cubed, x to the 4th plus, and then I'll have the list again. 1 plus x squared, x cubed, x to the 4th, on and on and on. Okay. Okay, now, the question of whether or not we're allowed to multiply these things together basically comes down to, are these series absolutely convergent or not? Okay, so if you think about it, the alternating guy, and I'll kind of write this up here, 1 over 1 plus x, 1 minus x plus x squared minus x cubed, dot, 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 dot. Okay, this is provided that the x is less than 1. Okay, well, if you take the absolute value of everything in here, the sum of the absolute value, -1 to the n, x to the n, that's just going to be the sum of the x to the n, which we know converges because x is less than 1. Okay, And so that means that this series is absolutely convergent, and so is this one as well. Okay, so because of that, we're allowed to multiply. All right, so I'm going to start looking at what I'm going to end up with. Okay, 1 times 1. Okay, now I'm going to get an x. Okay, now look in the multiplication and see how many terms are going to give us an x. There's going to be 1 times x, and then x times the 1. So it looks like there's going to be, come on, 2 x's. Okay, now let's look at x squared. Okay, yeah, sure. Didn't mean to erase that. X. Okay, so we're going to have x squared times 1, and then we're going to have an x times an x, and then we're going to have this 1 times this x squared. So now there's going to be 3 of them. Okay. And then as far as the x cubed goes, you had to guess for $1 million. Hopefully you'd say 4. Okay. Looks like it's going to be, for the x cubed stuff, I'm going to get 1 from this times this, 2 from this times this, 3 from this guy times this guy, and a 4th one from 1 times the x cubed. Okay, so the next guy is going to be 5x to the 4th. Okay, and so we see that we get the sum n equaling 0 to infinity, and then it's going to be, come on, n plus 1 x to the n. And sometimes people will relabel the counters. That's something that we'll be doing during our last week together. And if I want to start it at 1 and go to infinity, then I could say n times x to the n plus 1. But the main thing here is that this exponent has to be one less than what this coefficient is. Okay, so that's one way of doing this. And in additions past, he would cover things like, let's divide this power series into this power series. We'll do some of that stuff again as well. Okay. All right, so this is what we did. You know, we just multiplied the two things together. An alternative approach to this would be that to observe that if f of x is 1 over 1 minus x, f prime of x is going to be the derivative of the top, 0, times the bottom, minus the derivative of the bottom, minus minus 1, 1, times the top, all over the bottom squared. And that is this f of x that we were looking at. And so the derivative of the representation of 1 over 1 minus x would therefore be this 1 over 1 minus x quantity squared. The theorem from yesterday says that we're allowed to do this one at a time. And so what we end up with is the sum starting at 0, going to infinity, n x to the n minus 1. And since the n equals 0 doesn't provide anything, we can move it up to 1 to infinity, n x to the n minus 1. Okay, so there's a couple different ways to get these things squared away, you know. Okay, so as we go through all of the stuff that we're seeing in these problems, like if f of x was 1 over x squared minus 6x, you know, plus 2 or something like that, okay, then this also can be found using the geometric series. So what I'm going to do here is I'm going to complete the square in the denominator. So it's going to be I'll put the 2 there up front, and then it's going to be x squared minus 6x plus 9 minus 9. Okay, so by design, what we get is 1 over x minus 3 squared minus 7. Okay, and if I reorganize this, I'll say it's negative 1 over 7 minus x minus 3 squared. And then if I factor out a 7 out of this thing, maybe I'll factor out a negative 1 over 7 out of the denominator, and the negative 1 on the top, I'm going to get 1. And then this is going to be 1 minus x minus 3 over the square root of 7 squared. And so now we take negative 1 over 7 and we multiply it by the sum, n equals 0 to infinity of x minus 3 over the square root of 7 squared to the nth power. Okay, so I got negative 1 over 7. Then it's going to be the sum from 0 to infinity. It's going to be x minus 3 to the 2n divided by 7 to the n. And oops, switch back to the eraser. If I bring the thing in, it's going to equal, oops, I wrote equal sign. It's going to equal negative this series, 0 to infinity, x minus 3 to the 2n divided by 7 to the n plus 1. Okay, now, for what values is this valid for? So what we need to have here is the thing that's being raised to the n, x minus 3 over the square root of 7 squared, has to be less than 1. Okay, and so that means that 0 is bigger than or equal to x minus 3 squared over 7, and that's going to have to be less than or equal to 1, or less than 1. Remember, the endpoints don't count. Okay, so that's strictly like so. Okay, so that means that x minus 3 squared less than 7. So -7 less than negative square root of 7 less than x minus 3 less than the square root of 7. So that means the x can live in the interval 3 minus the square root of 7 to 3 plus the square root of 7. Okay. All right, now, if you look up here at the original guy, okay, and then compare with the series that we ended up with, and it's this one, we see that everything is negative. Okay, the squared thing here makes sure that nothing in there is going to be negative. So everything on the inside is going to be positive, and then I got this negative dangling outside. Okay, so let's start putting in numbers into the function. So it's f of x, x squared minus 6x plus 2.
So to sum it up, the 2n that's floating, it makes everything negative, and the negative that's outside the
No,
constant makes it everything positive.
the squared with the red arrow right there, that makes everything positive.
Oh, okay, I see.
And then the negative outside is just making, you know, the thing negative. All right.
Okay, I see. I had it back.
Okay, so back to the original function. The function was 1 over x squared plus 6x plus 2. Okay. Is that what it was? No, minus 6x. There I go, losing the minus sign. Okay. So let's do some experiments here. Like, what's f of 3 going to be? 1 over 9 minus 18 plus 2. That's negative. Okay. Yeah, this Dodgers game is just a pitcher's duel. Hardly any hits. Okay. Now let's get a rough idea how big the square root of 7 is. Okay, so square root of 7, bigger than 2, less than 3. Square root of 7, let's use this estimate, 2.64. Okay. I don't want to round up because I want to make sure I stay in the interval. Okay. So if we want to take f of 3 plus something that is very close to the boundary. Okay, so that's going to be f of 5.64. And so when I do that, I'll take 5.64, square it, and then I'm going to subtract off 6 times 5.64, and then I'm going to add 2. And what I get is negative 0.0304. It was exact. Okay. And then let's look at another thing that's kind of in there. Like, let's do the f of the 3 minus the 2.64. So that's going to be f of 1.64. And I think we don't even have to write this down. It's negative. Okay. All right. So when the negative first showed up, maybe you're thinking what might have been, okay, he made a mistake somewhere, because how can this thing always be negative? Clearly, there are values of x. We can plug into f of x right here to produce a positive number. But it looks like that when we're in this interval right here, everything turns out that it actually is negative. Okay, so now let's algebra this to death. Okay, the only thing that's deciding where this thing is going to be negative is where the roots are of this guy. It's not going to factor nicely, so we'll just use the quadratic formula. B plus or minus the square root of 36 minus 4 times 2, which is 8, all over 2. Okay, so x is going to be 6 plus or minus the square root of 28 over 2, which is 6 plus or minus, that's 4 times 7, 2 radical 7 over 2, which is equal to 3 plus or minus the square root of 7.
Hey, Bobby,
Uh-huh.
real quick, when you had that f of 3 minus 2.64, I know this isn't a big thing, but that's 0.36, not 1.64. Right?
Oh, yeah.
No worries. I know it doesn't matter. I just was looking at that and I was...
Brain fart. What's the subtraction?
That's 0.36.
0.36. Even more negative, you know?
Yeah. I knew it didn't make a big deal. I just wanted to fix that.
Okay, so now if you go back to your days in pre-calculus and whatever, wherever the hell these numbers are, 3 minus the square root of 7, and then 3 plus the square root of 7. Hold on, I gotta get my kids to turn the TV down. Okay, so we know that this is an up parabola if we were going to graph y equals x squared minus 6x plus 2. So it's going to go like this and go like that. Now notice, for all of the x values that live in here, they map to negative values. Okay, and this just so happens to be our interval of convergence. Okay, and so the negative sign I'm now not uncomfortable with anymore. I'm actually thankful that it's there, because it's doing what it's supposed to be doing. Okay. All right, so every now and then you get kind of strange results with some of these problems. And, you know, do a little digging and investigating, and this is what you end up with. Okay, so So let's try like one of these problems. Okay, so okay, timeout. Hold on. Shut up. Maybe I should just let them all beat the shit out of each other. Get it over with. Okay, so let's see if we can figure out something for this. So it's going to be, and I'm just going to make this problem up myself. Okay, it's x divided by 2 plus x to the 5th power dx. All right, no real good shot at doing a U substitution here. Trig substitution is out. This x to the 5th plus 2, that is going to have one real root, you know, the 5th root of -2. And the other roots are going to be all complex and stuff. So we're partial fraction stuff is going to be ridiculous. Now, sometimes you actually have to resort to that. I can remember at UCLA having to do that on an integral. And then, you know, we had these complex numbers in the partial fraction thing, and they ended up in logarithms. And we all know that, okay, if you try to define a complex logarithm, this is for Eduardo right now. Okay. And when you get this high and you're in complex analysis, okay, everything is the natural log. So we just write log. Okay. Now, this is supposed to be the inverse of the exponential function e to the z. But here you go, Eduardo. And for you guys that are going to be in Math 285 next semester, if z is a plus ib, then that's going to be e to the a times e to the ib. So that's e to the a cosine of b plus I times the sine of b. Okay. And what we end up finding here is that the function g of z is not 1-to-1 anymore. You know, I can let a be 0, and I can let b be pi over 2, and I get the answer I. And then I can let a equal 0 and b be 5 pi over 2, and again, it's going to be 0. I can let the a be 0, and well, you get the idea. Okay, so the log, because of this, it's technically not invertible. So what happens is you cut a branch out of it, and it's usually like the negative real axis. And so that's actually one of the books I'm working through my graduate thing. Okay, so what we're going to do here is we're going to take this function f of x that we're trying to integrate, x to the 5th, and we'll write it as x over 2 times 1 over 1 plus x to the 5th divided by 2. Okay, so now this is going to be x over 2 times the sum and equaling 0 to infinity of -1 to the n x to the 5n over 2 to the n. And so when I bring it back inside, the x inside and the 2 inside, 0 to infinity, negative 1 to the n, x to the 5n plus 1, and talking to some people, we're all really curious if you guys are going to be able to find technology that's going to do this.
I don't think so.
And then the other thing is that I really want you to try to not use it, okay? Because where we're going with this class, after we finish chapter 11, I'm going to go back to chapter 9, and then I'm going to introduce second order differential equations that used to be in chapter 17 in the book. And now they've deleted it, but it's kind of still on the COR that we're covering those second order differential equations with constant coefficients. So since it's online and who cares, and you guys will figure it all out, you might as well see it early and get a head start into Math 285. Okay. So anyways, this is the guy that we had. Okay. So now I need to integrate this 0 to 0.2, which is 1/5. I don't like decimals. I need to integrate this sum, 0 to infinity, negative 1 to the n, x to the 5n plus 1 divided by 2 to the n dx. And our result said that we can do this term by term. Okay, so it's equal to the sum, n equaling 0 to infinity. It's going to be negative 1 to the n, x to the 5n plus 2 divided by 5n plus 2 times 2 to the n, evaluated at 0 and at 1/5. Okay, so when we plug the 1/5 in for x, when I plug in 0, I get 0. I'm going to get this alternating series. 0 to infinity, negative 1 to the n. Okay, now it's going to be 1/5 to the 5n plus 2 divided by 5n plus 2 times 2 to the n. Okay, now hopefully you guys are starting to see that some of these random series that you get asked questions about aren't so random. Sometimes they come from problems like this. Like, what if we really needed to do this? What if we needed to figure out a number for that? You know, I can tell you as a double major, the math major in me says, hey, can you do that? Yeah. Have a nice day. Okay, I answered your question. But the physics people, they're the ones that have to get numbers out of this stuff. Okay, you can't just say, yeah, it converges. Okay, yeah, but converge to what, you know? And it might be that we get converging to a number that's not quite right. And so maybe then if this was our model for some phenomenon, we are not thinking about it correctly. So if we go back down here, go one last time, we get this, 0 to infinity, negative 1 to the n, divided by 5 to the 5n plus 2 times 5n plus 2 times 2 to the n. Okay, this is going to converge rapidly. Okay. And so let's say that we needed to estimate it. Estimate this integral 0 to 0.2 f of x dx with error less than, let's say, 10, 100, 1,000, 10,000, 100,000. I'd rather do a million.
Okay.
I like to have an even number of zeros. Now, when I put these kinds of things on exams, like in part 2 of the chapter 11 exam is when you'll be getting, you know, the questions like this. The question for tomorrow is basically come up with this. And I'll check, and everybody's going to be different. You guys will all probably be communicating somehow going, I don't know, man, I think I got this one wrong. You know, but anyways, I'll be able to figure out if you're right or not. Okay. Okay. So if you remember from our alternating series result, Rn, which is the error, it's the actual sum itself minus whatever we're going to use as an approximation. It's going to be less than or equal to the b first, the bn plus first term. Okay. So we'll write bn plus 1, which is all the positive stuff. So it's going to be a 1 over, okay, now this is going to be 5 to the 5n plus 7. You put n plus 1 into the n. Okay, you don't just add 1 to the exponent. Then it's going to be times blank. Oh, we might get one of these. So we're at the top of the 8th, it's 1 to 1. Just goes extra innings, we might get one of those goofy ass. You know how they're doing it now? It's like travel ball shit or high school stuff where when the games don't count, you know, it's not league games and it's in the off season, they'll have scrimmages where you start off with a 1-1 count and a runner on second sometimes.
That's so weird.
Yeah. And all the pitchers can't stand it because whoever's in the game, when you go to the top of the 10th,
Okay.
there's a runner on second. That's not his responsibility, you know?
Yeah,
And
he has to keep an eye on it. Then it's
yeah,
such a pain in the ass.
and so let's say a guy then, let's say there's a runner on second, you know, and like there is right now, and then the guy hits a single and drops him in. Okay, now he's not going to be charged with the earned run because that runner wasn't earned. Okay, but he is going to get tagged with a loss. And so they're only going to do this until the playoffs start, but I think it's kind of weird. Okay, and then I'm going to multiply 5n plus 7, 2 to the n plus 1, less than this 1, 2, 3, 4, 5. How many zeros do I have? 1, 2, 3, 4, 5, and 0. So then if I flip this whole thing over, 5 to the 5n plus 7 times 5n plus 7 times 2 to the n plus first power must be bigger than a million. If I did that right. 10, 100, 1,000, 10,000. Yeah, shit. 10, 100, 1,000, 10,000, 100,000, a million. Yeah, I'm right. Okay. Okay, now there's really no way to do this other than experiment. Okay, so just try some n. How about n equals 2? Let me just get out your calculator. Okay, so let's see here. When n is 2, that's going to be 5 raised to the 17th power. That's already massive. That's 762 billion. Okay, so that's way big. Okay, maybe if we let n equal 1. If I try n equal 1, it's going to be 5 raised to the 12th power. Okay, now that's 244 million, you know. What if we let n equal 0? If n equals 0, it's going to be 5 to the 7th power. Okay, that's kind of manageable. For n equals 0, that looks good. Now I'm just checking to see n equals 0, what happens there. So then this is going to be times 7 times, do that again, click, 5 to the 7th power, equals 78,000, times 7 equals, so now I'm at 546,000 times 2, I get 1,093,750. Okay, so what this says is that S minus S sub 0 is less than 0.2. How many do I have there? 1, 2, 3, 4, 5. 2, 3, 4, 5, 1. Okay, let's scroll back up a bit. There's our guy. So this is the downside of this. How do I remember this? Okay, so S sub 0 is the sum, n starting at 0 and ending at 0, of this -1 to the n. Okay, and then it's 5 to the 5n plus 2 times 5n plus 2 times 2 to the n. Okay, so S sub 0, I just plug it in. 1 divided by 5 squared times 2 times 1. That's 1 over 50. Okay, so that integral of where I, way back when I started, there it is, right there. Okay, I want to be able to integrate x divided by 2 plus x to the 5th from 0 to 0.2 dx, and this is approximately equal to 1 over 50, which is 0.2. And we know that we are correct to within 6 decimal places. Okay, so this is the kind of stuff you really like. When you've got a seemingly big tolerance, or seemingly small tolerance, and you only have to use the first term. That's kind of cool. All right, only had to use one term.
Isn't 1 over 50 0.02?
Is it? Oh yeah. 0.02. Okay. So if you have some kind of a device that can numerically integrate this, and my TI-80 whatever calculator won't do it. Now I downloaded a better calculator on my phone. So let me see if will it let me integrate? Let me see. Where's the function? if you have if any of you guys have a TI 83, 84, 85 calculator, what you do is you go to the catalog of functions and you look up this guy, fn int, written in lowercase letters. You hit that button, and then it's going to ask you, okay, what's the function? What's the letter that you're integrating with respect to? I don't know why that step's in there. And then it asks for the lower bound, and then it asks for the upper bound. And then you hit enter, and it'll chew on it for a second. And, you know, give you your, you know, the numerical thing. Now, I don't know what program they're running. There are so many, just at Cal Poly alone, so many of the people that were kind of like Brian, that, you know, they'd gone to school and they were coming back to do a master's, and they were doing it in math for various reasons. You know, it could be that, well, I remember this one guy in the suit that came every morning in the analysis course. He was trying to get a master's degree in statistics. And sometimes, you know, you have like high school teachers, and if you get a master's in your subject, you know, you get a raise. Didn't see very many of those because Cal State Fullerton has that program, and it is a complete joke. Anytime I'm on a hiring committee and I see that the person that I'm evaluating came from Cal State Fullerton, I take their packet. Back then it was packets, now it's online, but I'm going to look more closely at that. They do classes like this, like instead of actually hardcore doing all this stuff that we're doing right now, what they do is they kind of talk about what happens. And, you know, if we were actually doing this, you would see this. So it's like it's a joke. And there's a lot of people out there that's their master's degree. And it's just you're not forced to learn anything. So a lot of them don't. Now, they also have a regular master's degree at Cal State Fullerton. And so that's why I always segregate those applications, because I want to see, okay, does this person have the real one or the fake one, you know? All right, there was an application of that. Got a problem here. Still haven't gotten any text from my daughter yet. So it looks like she's not done over there. A lot of times they let her stay after and hit with the older kids, because even though she's maybe a couple years younger, she's a better athlete than most of those girls over there. So we want to show that pi equals 2 radical 3 times this infinite sum, n equaling 0 to infinity, and it alternates -1 to the n divided by 2n plus 1 times 3 to the n. Okay. So this is a representation of pi. Okay, now I realize that this, you know, a lot of this is dated kind of reasoning here because of cloud computing and stuff, but you still have standalone computers where, you know, there's no cloud. At least I would hope that our national security agency isn't using the cloud to, you know, crack codes and figure out when the next terrorist attack is coming. So if you have a series that represents these irrational numbers, what you can do is just enter it in or just carry the symbol along with you, okay? And then when you need it, you can figure out how many terms you need to approximate. Does that make any sense? Okay, now he gives us a clue here. We need to start with tan inverse of x. Okay, so solution here. Now, I've never in my life done this problem. So, first time. F of x equals tan inverse of x. Okay, so f prime of x is this 1 over 1 plus x squared. And f prime is this sum, 0 to infinity, -1 to the n, x to the 2n. So this means that f of x, which is tan inverse of x, has this series where I just integrate term by term that guy. 0 to infinity, -1 to the n, x to the 2n plus 1 divided by 2n plus 1. So this is the series for tan inverse. Okay. So let's see here. For tan inverse, we start with the tangent function, okay? And all of the restrictions that we put on the tangent function now cannot be changed, okay? The principal place to graph the tangent function is in between the asymptotes x equals pi over 2 and x equals -pi over 2. And the graph of it goes like this, comes down. So there's our tangent graph. Okay. So how are we going to get something out of this? Let's see here. So something's going whack on my thing. Come on, draw. Okay. All right. So now we have our series for tan inverse. Okay. So what? Okay. Now it kind of looks like something's going on here, right? With the similarities here, you know, there it is. There it is. So let's just start like thinking, where would a 3 come from? You know? So if we start by looking at some numbers, like for example, the tan inverse of 1, which is going to be the sum from 0 to infinity of -1 to the n over 2n plus 1. What is the tan inverse of 1? Pi over 4, right? When you go to graph the tan inverse function, let me do this guy again. I'm drawing at an angle since I'm clicking. Okay, so if I graph the tan inverse guy, and then like that. Then we've got Now the asymptotes are going like this and like this. And the graph and go down like this and like that. Okay, so on the y-axis, the asymptote here is pi over 2, negative pi over 2. Okay, so pi, how am I going to get a 3 to the n out of that? Where'd the radical 3 come from? See, here's why they're doing this problem. As we've seen, this series right here is conditionally convergent. Generally, conditionally convergent series take a long time to add up. You know, if you know, we've proved that the natural log of 2 is this alternating sum, 1 to infinity, negative 1 to the n over n. Okay. And so if I'm gonna truncate it off somewhere and estimate it, then the error, dang it, the error is going to be less than 1 over n plus 1. Okay, and so if we want this to be smaller than what we had last time, the n plus 1 is going to be bigger than 1,000,000, right? In the previous example with the integral that I did, it converged to within this tolerance. All I had to use was the first term of the infinite series. Okay, this one now I'm going to have to use the first 1,000,000 terms to find it. This series, however, looks like it's gonna be converging more rapidly. Okay, so what do you think? Nobody's into this right now, huh? Everybody,
It's like, it's more rapidly, right? Because it's shorter, it's thinner.
yeah. The fact that I have a 3 to the n in the denominator up here is telling me that this is going to converge a lot more rapidly. Okay, because it's going to be absolutely convergent.
Mm.
Just you know, check it out. So I'm trying to figure out what we need to plug in to get that. Okay, so let me write the tan inverse guy down again. Tan inverse of x is equal to this sum, n equaling 0 to infinity, negative 1 to the n, x to the 2n plus 1 divided by 2n plus 1. Okay, so start doing some angles here. Let's see here. If I had the, let's say that this was a 30, 60, 90 triangle, then this would be 2, this would be 1, and this would be the radical 3. Okay, so looks like this triangle's somehow involved, okay? And we're trying to show that pi can be represented by the 2 radical 3 times the sum from 0 to infinity, negative 1 to the n, over 2n plus 1, 3 to the n. My daughter found my ride home. All right, bottom of the knife, Kenley Jensen's in. So if he shuts them down, then we go to that weird runner on second deal. Okay, so let's see here. 2 the tangent of pi over 3 is going to equal radical 3, right?
Yeah.
Mm-hmm. And let's see, how am I gonna get the 2? The sine of 30 is 1/2, so the cosecant, okay, let me kind of move the triangle around here. So the tangent of pi over 3 is that. So that means that the tan inverse of radical 3 is equal to pi over 3. And there's one idea in here that I'm missing. Tan inverse of that is that guy, okay? And, so where's the 2 coming from? I do pi over 2. This is the tan inverse of infinity. That's not helping. No, I think I stumped myself. So let's see here. So if I plugged in the tan inverse of radical 3, then I'm going to get the sum n equaling 0 to infinity, negative 1 to the n, radical 3 to the 2n plus 1 divided by 2n plus 1. And just keep playing around with it. The sum 0 to infinity, negative 1 to the n, then it's going to be a 3 to the n, and then there's a radical 3, and divided by 2n plus 1. Okay, so at least we've got something going for us here. I can take this guy out, 0 to infinity, and then it's going to be negative 1 to the n, 3 to the n, divided by 2n plus 1. Okay, so we've got the 3 in the numerator, and it needs, according to the problem, needs to be in the denominator. So let's see here. What could I do? That is equal to pi over 3. And oh, I get it. Okay, we're not allowed to use this because if we go back up to how we got the tan inverse, it started all the way back up here, okay? And so we know that the x in magnitude has to be less than 1. Okay, so here's 1, here's negative 1, and that's pi over 4. And this is negative pi over 4. The x's that we're allowed to use are these blue guys. They can go here, all the way to there, to there. So radical 3 was too big. Okay, it's sitting out there. Okay, so back to our dilemma here. Let's see. Oh man, you guys, there's the error. Duh. Okay, so we have it. Ready? Okay, so the here we go. The tangent of pi over 6 is equal to 1 over radical 3. Okay, so that means that pi over 6 is equal to the tan inverse of 1 over radical 3. Now I just got a text. And now it looks like I have to go get her in a few minutes. Okay, well, let's see, make some headway on this before. She said she'll be ready in 20. Takes me about 10 minutes to get over there. Okay, so the series is for tan inverse. Every time I say series. What? Where was my, so it's going to be the negative 1 to the n n equaling 0 to infinity, -1 to the n. Okay, now the x, which is 1 over the square root of 3, it's going to get raised to the 2n plus first power divided by 2n plus 1. Okay? And so this is the sum from 0 to infinity and beyond, -1 to the n. Now all of this action will be taking place downstairs. The square root of 3 to the 2n plus 1 times 2n plus 1. So that's the sum from 0 to infinity, -1 to the n. Okay, now there's going to be a radical 3 to the first power, and then a radical 3 to the 2n power times 2n plus 1. So this, I can bring the 1 over square root of 3 out of this guy and add it up as -1 to the n divided by 2n plus 1, and then a 3 to the n. Okay, now that's what they're telling us. Okay, so this is pi over 6. So that means that pi is going to be 6 over radical 3. You guys thought I was going to give up, didn't you?
A quote from my favorite sci-fi movie: "Never give up, never surrender."
Okay, now I bet if we rationalize this denominator, 6 over radical 3 over radical 3. So that's going to be 6 radical 3 over 3, which is 2 radical 3. So we got it. Okay, now before we leave this problem, let's see how rapidly this thing will converge. Okay? So let's say that I want to estimate pi, and I want my error, the magnitude of the error, to be less than, let's say, 1,000, 10,000. Okay. So again, since it's an alternating series, the Bn plus 1. Okay, now notice that this is this absolutely convergent? An plus 1 over an. It's going to be 2n plus 3, 3 to the n plus 1 divided by 2n plus 1. Wait a minute, I'm doing that wrong. Okay, so an plus 1 over an, that's going to be 2n plus 3, 3 to the n plus 1, and then it's going to be 2n plus 1, 3 to the n. That is going to cancel with this, And so I'm getting 2n plus 1 divided by 6n plus 9. That goes to 1/3, which is less than 1. So that means it's absolutely convergent. Okay, so we should suspect if it's absolutely convergent that it should kind of go fairly rapidly. So take our bn plus 1, which is 1 over 2n plus 3, 3 to the n plus 1, and set it less than 1 over 1,000. Now, what I do on tests with these guys is I have the bounds be like 24 over 1,000 or 1 million or something, because I know I'm just trying to make you have not gnarly numbers. Oh, Jansen's blowing it. There's 2 runners on, but 2 outs. Okay, so this means that 2n plus 3 times 3 to the n plus 1 has to be bigger than 1,000. So now we just start experimenting. Let's see. So let's try n equals 3. Okay. So I'm going to have 3 to the 4th power is 81 times 9, and I get 729. Okay. I get 729. So if n is equal to 4, let's see if it works. It's going to be 3 to the 5th power, 243, times 11, and that does it. So 2, 6, 7, 3. Okay, so we're going to use S4. Okay, now eventually, like next week when we're doing the sine and cosine stuff, those guys jump from like the sine is an odd function. All of the powers in the expansion are going to be odd powers. So the even powers are there, they just have a coefficient missing. Okay, so when I'm saying how many terms do you need, you don't need n terms, you need to use Sn. And depending on where this S sub 4 started, okay, it's going to be the sum n equals 0 to 4, negative 1 to the n, over 2n plus 1, 3 to the n. There are 5 terms here. Okay. Now, let's say that I changed the tolerance to 1,000,000. Okay. So if that number had to be bigger than 1,000,000, if we use 5, let's see how much 5 gives us. So 3 to the 6th power equals 729. That's not going to do it. 3 to the 7th power, 2,000. That's not going to work. 3 to the 10th power. Okay, now we're getting somewhere. 3 to the 12th. Looks like for 1, 2, 3, 4, 5, 6, looks like we would use n equaling 12. I think that's what I just figured out. Because if I go, no, use 11. Come on, right. And equals 11. Okay. All right. So that being said, there's an example of using this stuff in action. Okay. So stop the screen share. All right. So tomorrow, guys, I'll log into class as usual. And if you have questions, you know, I'll be here to, to answer them. Oh, there we go. Turn around a second.
So tomorrow's just kind of like the first test. It's just a test day, really.
Yeah, just a test day. Okay.
Cool.
Yeah, my call. Yeah, a few of the other people are kind of curious to see, like, are you really going to get this, or what's going on? All right, guys, I'm going to pick up my daughter. So you guys have a great night, and maybe see you tomorrow. Go ahead and email me if you have any integral questions or series questions. Peace out.